Welcome you all for this channel. Next we are going to discuss the concept that is symmetrical fault. So it is mentioned that there are different type of fault which is occurring in a system, broadly classified into two different type. One is symmetrical fault, another one is unsymmetrical fault. So other than this, we do have some other type of fault, that is shunt fault and the series type of fault. So whereas in case of the shunt type fault, it involves the short circuit between the conductors or between the conductor and the ground. So they are characterized by increasing current and fall in voltage and the frequency. So there are the different type of shunt type fault are single line to ground fault. Generally it is called as LG, line to line, then double line to ground fault, and three phase fault. So other than this shunt type fault, we do have series type fault. So that is nothing but when one or two lines in a three phase get open while other lines or the line remain which is intact, such called series type of fault. So here we can see to that they are characterized by increasing voltage and frequency, and there is a reducing in the current in the case of the faulted phase. So they can be grouped into, that is, one conductor open fault, two conductor open fault, then three conductor open fault. So here we discuss that about the three phase fault. Although these are falling under the category of the shunt type fault, the three phase are symmetrical. So it means that it involving all the phases are equal. So the fault current is same in all the three phases, and hence the system remains the balance after the fault which is occurring. Already we gain the knowledge of the voltage and the current in one phases, which is sufficient to determine the voltage and the current in other two phases, because we are considering that is symmetrical in nature. So in the case of the unsymmetrical fault, what will happen? The fault current will not be remain the same. So hence the system is said to be rendered unbalanced. So it is nothing but it involves the lot of the phase of the different magnitude and the phase angle for the each phases. So analysis of this unbalanced condition can be carried out on a three-phase basis, but this is very cumbersome process. So there is a simpler approach. It is used to method for the symmetrical component and symmetrical networks for determining the voltage and current in all parts of the system after the occurrence of the fault. So it is to be noted that the three-phase fault can also be analyzed using symmetrical component, though it is not a common practice to do so. So we are going to analyze the various type of the fault, means the unsymmetrical fault, so in this chapter. Okay, so before that we can understand, so what is the possibility of the occurrence of the fault, that is unsymmetrical fault in the nature. Okay, so we can see to that there are the four different type. Single line to ground fault, the possibility of occurrence is 72, 85 percentage. Line to line fault, it is 8 to 15 percentage, and double line to ground fault, it is 4 to 10 percentage, and the three phase fault is 3 to 5 percentage. So here, so how we understood that in the previous chapter, means the symmetrical fault on generator, then the transmission line. Okay, the same way we are going to understand so these unsymmetrical fault on these equipment. Okay, first let us know that fault calculation on synchronous generator, means the first component what we considering. So consider that the balanced three-phase system, so that is the synchronous generator, which is subjected to some unsymmetrical fault that is F across the terminal. The fault may be unsymmetrical one, but to the left of the point F, the system is completely symmetrical. Hence, in this condition, the current of the given sequences produce the voltage drop of the same sequence only, means the sequence impedances are uncoupled. It is not depending upon the other phases, since the alternator generator means the alternator generates balanced voltage only. So from this we can understand that regardless type of the fault, the terminals of the generator will become VA1 is equal to EA1 minus IA1 Z1. Okay, so that is VA2 is equal to, okay, so here VA2 is equal to minus IA2 Z2 and VA0 is equal to minus IA0 Z0. Okay, now let us understand the first step fault in on the case the generator, that is single line to ground fault on an unloaded synchronous generator. Okay, assume that the phase A is one of the fault which is occurs, okay, means the grounded. So here you can see to that A, B and the C and the neutral having the impedance the value of Zn. Okay, so here it is a meaning that we are assuming that the phase A, it is grounded and it is short circuited directly to the ground. Okay, so based on this we can understand that the terminal conditions, so this is very important. So based on this only we are going to we are going to derive a lot of the conditions. Okay, the terminal conditions. So it is nothing but based on this we can write it as VA is equal to 0, okay, and the IB is equal to 0 and the IC is equal to 0. So it is a meaning that, so where does the fault which is going to take place, the voltage, if it is grounded, the voltage will become 0 and the healthy part of the other phases of that the current is going to be 0. It means that if the fault is takes place in phase A, the voltage across the phase A is 0 and the current across the other two phases will become 0. Okay, so based on this, where the fault, it is the fault is across the phase A, so voltage will become 0 and the current across the B and the C will become 0. Okay, so these three terminal condition in terms of the line current and the third phase voltages are to be transferred to the condition in terms of the symmetrical components. Okay, so that is nothing but here, so there are the two things we need to understand here. Either we should transfer the voltage, means the phase voltage in terms of the symmetrical component, or the phase current in terms to the symmetrical component. So here, so based on the terminal condition only we are going to derive the symmetrical components. Okay, you can see to that here the IB and the IC is 0. So based on this it is going to be very easy for us to calculate the symmetrical component for the current. Okay, because the two phase value of the current means the two phases where the value of the current is 0 and here for the voltage is only one condition is 0. Okay, so suppose if the two phase voltages is 0, okay, then we can go for the phase voltages. Okay, so here this value is the phase current is 0, okay, IB and the IC is 0, so that's why we are calculating the value of the current, means the symmetrical component value of the current we are going to find it. So we know that the equation IA0, IA1 and IA2, so that is nothing but the symmetrical value of the current is equal to 1 by 3 times of 1 1 square 1 a square a to the IA0 IA 0, this is 0. Why? Because why we are rating this is IB and the IC is 0, because based on the terminal conditions. Okay, so doing my means by multiplying this we can write it as IA0 is equal to 1 by 3 times of IA plus IB and the IC. So that is not IB and the IC value 0. So we'll get 1 by 3 times IA. For the IA1 it is 1 by 3 times of IA plus A into IB plus A square into IC. So again B and the C values are 0. We'll get 1 by 3 times IA. Similarly for the IA2 we'll get 1 by 3 times of IO. So from this equation we can write it as IA1 is equal to IA2 is equal to IA0. That is 1 by 3 times of IA. Okay. So this is call this equation as 1. So we know that what is VA. It is from this we can understand, means from the equation 1 we can understand that there is a presence of the 0, positive and negative sequence value of the current which is present. Okay, so we know that what is the terminal condition, VA is equal to 0. So we know that we are transferring the phase voltages in terms of the symmetrical component. So that is nothing but VA0 plus VA1 plus VA2 is equal to 0. So call this equation as 2. From equation 1 and 2 we can notice that, okay, so the current is remains the same, okay, the voltage is going to add up. So from this what we can understand here is this is that the symmetrical sequence network means the internal interconnection sequence network is said to be connected in the series. Okay, so based on that we can write it as interconnection sequence diagram. So that is nothing but this is VA1, so this is VA2 and this is VA0. So we can here see to that what is a VA1. VA1 is equal to, we already understood that it is can be written as EA1 minus IA1 Z1. Okay. Similarly for the VA2 it is minus IA2 Z2 and for the VA0 it is minus IA0 Z0. Okay. So write this. What is VA1? It is EA1 and Z1. Okay. The current is IA1. Similarly for the VA2 it is Z2 and IA2. Similarly for the VA0 it is Z0 and IA0. So here you can see to that what is Z0 value. Z0 is consisting of Zg0 plus 3Zn. Already we derived that. Why we are considering it is 3 times of the value of the Zn. Okay. So you can see to that what is the value of the IA1 is flowing, the same current which is flowing across the circuit across the VA2. So it is going to become IA2. The same amount of the current which is flowing into the VA0 circuit. So this will become IA0. So based on this we can write these sequence quantities with the help of the interconnection sequence network diagram. Okay, what is IA1? It is same as IA2, that is same as the IA0. Okay, what is the source of EMF here? Only we have that is EA1, that is equal to EA. Okay, divided by total impedance of the network. What is that? It is Z1, Z2 and Z0. Okay, so the current we are going to calculate will become the source of EMF divided by total impedance of the network. So already we know that what is VA1. VA1 is equal to EA1 minus IA1 Z1. So from where we got this? Already we derived that, okay, in the previous chapter. So based on this we are going to consider. So VA1 is equal to EA1 minus IA1 Z1. Substitute this. What is IA1? IA1 is nothing but it is this. Okay, this value. Okay, so substitute this IA1 value here. Okay, and do the simplification. After doing the simplification we will get, okay, substitute this. What is IA1? It is EA divided by Z1 plus Z2 plus Z0. Okay, after doing the simplification we will get EA, it is multiplied by Z2 plus Z0, okay, divided by Z1 plus Z2 plus Z0. Okay, and similarly we are going to calculate what is the value of the VA2. VA2 is nothing but IA2 Z2. Okay, so substitute that. What is the value of, okay, what is the value of IA2? IA2 is nothing but this equation. Okay, so this equation EA divided by Z1 plus Z2 and Z0 multiplied by Z2. So we will get the equation will become, okay, EA multiplied by Z2 divided by Z1 plus Z2 plus Z0. Similarly VA0 can be written as IA0 minus Z0. Okay, substitute this. What is IA0 value? IA0 value is same. Okay, EA divided by Z1 plus Z2 plus Z0. Okay, so it is nothing but EA multiplied by Z0 divided by Z1 plus Z2 plus Z0. Okay, so here, so these are in terms of the symmetrical quantities. Okay, So actually we are going to calculate the fault current. Where is the fault which is takes places? Means the fault which is takes places across the phase A. Okay, across the phase A. So that is nothing but IF is equal to IA. So that is equal to 3 into IA naught. From where we got this IA naught value? Okay, from the equation 1. Okay, means from already we know that. Okay, it is IA is equal to IF is equal to, it is 3 times of IA naught. Okay, from the equation 1 we can write it as, what is IA naught? So here what is IA naught? It is EA divided by Z1 plus Z2 and Z naught. Okay, so here, so basically we are trying to calculate, means we are trying to calculate the equation considering the value of Z naught. So it is a meaning that we wanted to know whether if the system is grounded, okay, if not grounded, what is going to happen in the case of the fault current during that fault condition. Okay, let's consider with help of this equation. Okay, in the case of generator, if it is not grounded, we know that what is Z naught? Z naught is equal to Zg naught plus 3Zn. Okay, so if it is not grounded, so this will become, it is trying to become infinite. Okay, this value Zg naught is very small compared to the infinite, so it will become infinite. So substitute this value IF, okay, to this equation. Okay, what will happen? Z naught, if it is become infinite, the fault current will become 0, because 1 by infinite will become 0. Okay, so these are the conditions we need to satisfy.